In this video, we continue with chapter 4.7, and we're going to take a look at some examples of transition matrices. So we have our two bases, B, which consists of vectors v1, v2, and v3, and B prime, which consists of vectors u1, u2, and u3. So we are going to write our matrix equation that tells us how to change from coordinates relative to B into coordinates relative to B prime. So our relationship is that P is this matrix that when we multiply it by the column vector x in B prime, so the coordinates relative to B prime, we get out the coordinates relative to B. So in our example here, this is matrix P. C1, C2, and C3 are the coordinates relative to B prime. That's our unknown values. And then this is C1 times the 101, because if you think about multiplying this through, all of these elements in the first column are going to get multiplied by C1. This says C2, I had to correct it, multiplied by the values in column 2. When we multiply through, you can verify that these constants multiply through each column in this way. And then we have C3 multiplied by the values from column 3. And then that's going to equal our column matrix here, and that is x relative to B. So P is known as our transition matrix, where x, and this is an and symbol here, x relative to B prime and x relative to B are the coordinate matrices of x. So we use matrix P inverse to transition from B to B prime. So P takes us in one direction from B prime to B, and P inverse takes us back from B to B prime. So we can go in either direction. And it doesn't really matter if you call your matrices B and B prime, or we use the standard basis. We call the basis S. So it doesn't matter what values or letters you use for your basis here. We're going to use B because B is short for basis. So we're going to head over to SIMPy and find the transition matrix. So essentially, we're going to take matrix P here and find P inverse. So I'm going to pause recording and head over to SIMPy and restart recording over there. Okay, so here we are over in SIMPy. And so now in SIMPy, we are going to take our matrix P and find the inverse. So I'm going to call my matrix P. I think SIMPy is okay with me using letter P in the matrix. Sometimes SIMPy doesn't like certain values. So the first row of matrix P was 102. And then the second row is 0, -1, 3. And the third row is 1, 2, and -5. All right, and oh, it doesn't like P, yeah. So I'm going to use a different letter. I'll just call it M. Unless I made a typo in here somewhere, but I think it just might be the choice of letters. Oh, actually it's a typo. If you see here between the 0 and the -1, I forgot a comma, so we'll see here. Now it looks like SIMPy is okay with us using P for matrices. Okay, so matrix P checks out. I copied it correctly. Now I'm going to do the inverse. So remember that's P star star for an exponent and a -1. Even though an inverse isn't an exponent, in code we still think about it as the same symbols as when we're calculating an exponent. So here is our inverse matrix for P. So we are going to use this in our transition matrix when we move backwards. So I'm going to pause again and head back to our example. Okay, so we calculated P inverse using SIMPy. So we see here's our matrix P inverse now right here, and we see it's a match for our calculations in SIMPy. So now we're working this equation to try to find x relative to the basis B prime. So our calculation is going to be P inverse multiplied by x relative to the basis B. So that's this column matrix corresponding with the vector 1, 2, -1. And that came from our equation in the previous slide. That was what our initial equation was equal to, x relative to the basis B. So now to calculate our transition matrix, we take P inverse multiplied by our vector column matrix 1, 2, -1. You could multiply it out by hand like I did here. You can also verify in SID-B. So it's going to work out to be 5, -8, and -2. So that is our vector or column matrix X relative to basis B prime. Or you can think about it as our coordinates in R3 relative to basis B prime. So for our general basis B and B prime, this is the formula we're going to use for our transition matrix from B prime to B, P. We're going to put in the 3x1 column vectors from each of B prime. So if you look back here, we called the B prime basis U1, U2, U3. And then P is always going to be a square invertible matrix. So we'll find its matrix inverse and work through this formula that we did here to find X relative to B prime. So let's take a look at an example. So here B prime is U1, U2, U3, where U1 is 1, 2, 0, U2 is 0, -2, 3, and U3 is -2, 1, and 0. We're going to let S be the standard basis. And then X relative to the standard basis is 3, -1, and 3. So when I say S is a standard basis, just to clarify, in R3, that's the vectors 1, 0, 0, 0, 1, 0, and 0, 0, 1. Okay, so our solution is we're going to let X relative to B prime be the scalar C1, C2, C3 that we're going to solve for. So then the coordinates is going to be C1 times U1, C2 times U2, and C3 times U3 after we do our multiplication through. So X relative to the standard basis is going to be C1 relative to U1 standard basis, C2 multiplied by U2 relative to standard basis. I meant to say C1 multiplied by U1. I think I said relative to. And then C3 multiplied by U3 relative to the standard basis. So we know that is going to look like this. Here is X relative to the standard basis. Here is matrix P, and then here is X relative to the new basis B prime, which is our inverse. So to do our calculations to find that, X relative to the new basis B prime, or those scalars C1, C2, C3, we're going to multiply P inverse times X relative to the standard basis. And so we get out here 1, 1, and -1. And those are our scalars. So you can think about X relative to the standard basis as just a normal coordinate plane, and the coordinates aren't rotated or stretched or compressed at all. Okay, in the next section 4.8, we're going to be looking at applications. So we'll be using some of these change of basis techniques with conic sections to do some rotations and see how this can be applied to geometric representations.